Hi, I'm Chunyuan.
And I'm Jason, and today we're going to tell you a simple way of measuring an interesting property of neural networks. In typical neural network training, we randomly instantiate a network's parameters and then optimize them to minimize some loss. If we imagine we have parameter space in front of us, we can think of this as choosing an initial point in that space and then slowly following gradients from that point to one with a lower loss. In this paper, we modified this procedure just slightly. We choose the initial point in the same way, but then instead of optimizing in the full parameter space, we generate a random subspace around that initial point and allow the optimizer to move only in that subspace. Concretely, from the initial point, we generate a set of random directions, and then motion is allowed only in the space spanned by those random directions.
So, how well will this work? Well, it depends on how big the subspace is. On one stream, dimension 1 would just be a line search in a random direction, and the chances are we would never find a good solution. On the other hand, if we use enough vectors to span the entire space, it's guaranteed we could find any available solution. So the key idea of this paper is to carefully increase the size of the space. As we grow it, we generally observe a transition from networks that do not work to the ones that do. And we call the dimension at which this occurs the intrinsic dimension.
So, for the rest of this paper, we take this new tool around, and we use it to measure a lot of networks and see what we can learn. First, let's try a 3-layer fully connected network on MNIST, say one with layer sizes 784, 200, 210. This network has a full parameter space of about 200,000 dimensions. So if we measure its intrinsic dimension, what do you think we'll get? It turns out that this network starts working well at an intrinsic dimension of about 750. So maybe the first salient conclusion is that 750 is pretty small. We've somehow found a fairly accurate network using only 0.4% of the available degrees of freedom. This is even smaller than the number of input pixels, which in the case of MNIST makes at least some sense, as a lot of the input pixels are just always off. So let's think about what else this number 750 means. So imagine we were in 3 dimensions, and by using a random one-dimensional line, we managed to run into a solution. So barring extremely lucky scenarios, we would know that the solution we found must have at least 2 dimensions. So, in 200,000 dimensions, if we found a solution by using 750, it tells us something basic about the solution set we've run into. It tells us the dimension of this blob of solutions that we found must be at least 199,250. In other words, we've found a big solution, one with a lot of redundancy, or with many directions in which we could travel and still remain on the solution set.
Next, let's try something else. Let's take the same network, but now make each hidden layer a little wider, say 225 instead of 200. If we measure the intrinsic dimension of this network, surprisingly, we find again about the same number, 750. In fact, we still find about 750 if we make the network much wider, or even if we add a few more layers. So, what does this mean?
So first, it means that this quantity we're measuring, intrinsic dimension, is a fairly stable metric across a family of models, or at least across this family for this dataset. Second, and this is one of the coolest parts, it says something beautiful about what happens to the objective landscape as we add more parameters to this network. Because the intrinsic dimension isn't changing, it shows us that every new parameter we add, every extra dimension we add to the native parameter space, just goes directly into increasing the redundancy of the solution set by 1 dimension. So many researchers have noticed that larger networks can be easier to train, and this result suggests a possible reason why. As we add more parameters, we increase in some sense how much the solution set covers the space. There are definitely some subtleties here, so do check out the paper for caveats.
Another angle to consider is model compressibility. It turns out, to check our point and then reconstruct one of these models, we only need to store a single seed for the random subspace, and then the 750 learned parameters. This means the model can be compressed, in this case, by quite a lot. This isn't necessarily the best compression model out there, but it is very simple. Any end-to-end parameterized model can just be trained end-to-end in a random subspace instead. We can also think of this as a way of upper bounding the minimum description length, or MDL, of the model. If you are familiar with Occam's razor, which states the simplest explanation is usually the best one, MDL is similar, all else being equal. Models with smaller MDL are preferred.
Alright, so enough of this same FC network. Let's try some other combinations. If we make our network convolutional, we now measure a much smaller intrinsic dimension of 290. So using our MDL argument, this suggests that COM nets are better than FC nets for this task, a result which will probably surprise no one. However, Are convets always better? What would happen if we shuffle the input pixels, as done in Zhang et al. From ICLR last year? The FC network is permutation invariant, so it has the same intrinsic dimension of 750 as always. However, if we measure a convet on this task, we now find that the intrinsic dimension jumps all the way to 1400, which is way higher than the FC version. So we find convets are better until we break the assumption of local structure, after which they're measurably worse models. In general, in more complex situations where we're not quite sure what model is best, we can imagine using measurements of intrinsic dimension to guide our search. For example, in a world where we train larger and larger models consisting of many submodels and train using many losses, designing architectures for submodels may not always be obvious, and considering intrinsic dimension may prove useful. Alright, so what about the experiment from Zhang et al. With randomly shuffled labels? We trained a network to memorize 5,000 randomly shuffled labels, and we found this requires a very large intrinsic dimension of 90K. So this is much higher than we've seen before, and it reflects the fact that the network needs a lot of capacity to memorize each random label. In this case, it works out to 18 degrees of freedom for each label. If we train on 10 times more data, we find as expected that intrinsic dimension grows. However, it grows only to 190K, so it's larger, but it's not that much larger. In fact, now we need only 3.8 parameters per memorized label. This is kind of an interesting result where we observe something like a generalization, but here it's generalization from one part of the training set to another, even though the labels for that training set are just random. It may be that training on some random labels forces the network to set up kind of a base infrastructure for memorization, and that this infrastructure is then used to make further memorization more efficient.
Alright, we just spent a long time talking about MNIST. In the paper, we show results on a lot of other tasks, which we will only briefly summarize here. We took measurements on CFR10 and we found it's roughly 10 times harder than MNIST for both FC and convets. We're also trying to measure the intrinsic dimension on ImageNet, but we pretty much failed. We were able to take advantage of this beautiful efficient projection method called fast-fold transform, but our implementation was not fully optimized for GPU, so it ended up too slow. Future work.
So you erase now. No, sorry. Actually, don't erase. I'm just gonna stop. So as you might imagine, the whole subspace training approach can be applied just as easily in reinforcement learning settings. In the paper, we trained networks using both ES and DQN, and we found one can get a humanoid to walk in about 700 dimensions, and can play Atari Pong for pixels in 6,000. So these tasks require roughly the same capacity as classifying MNIST and CFAR respectively. These relatively low dimensions may be why random search and gradient-free methods work as well as they do. So finally, we'll leave you with one last result, which is on the pole balancing problem. This problem requires that an agent balance a pole by moving the bottom left and right. It may seem like this is challenging because it's tricky for humans to react quickly enough to keep the pole balanced. But it turns out that for an agent without slow reflexes, it's actually incredibly simple, with solutions being found in only 4 dimensions. This is sort of comically small. It's 100 times easier than MNIST, and it's something we should probably keep in mind when spending time on toy problems.
Alright, thank you for listening. If you are interested in learning more, please check out our code and paper. In the paper, we took measurements. Oh, really? Oh, shit.
This problem requires that an agent balance a pole by moving the bottom left and right. This may seem like it's tricky for humans because it requires faster balance a pole by moving the bottom left and right. This seems like it might be challenging. This seems like it might be challenging because it's tricky for humans to react quickly enough to keep the pole balanced.